Hello and welcome back to another episode. Today we're going to be talking about quantum physics, the A-level syllabus. This is a relatively simple syllabus. However, in the recent years, we've seen some very difficult questions in some of the A-level exams. The couple of first things you got to know, it really starts with the idea of the photoelectric effect. So you have to know things regarding that. But today we're going to be discussing mostly how you can calculate the energy of a photon or a particle, a fundamental particle of light. Of course, we have the idea of whether light is a wave or a particle, but we're not going to get into those discussions today. We're just going to be quickly doing some questions and talking about some of the main things you have to know. So the first thing you have to know is that if you want to calculate the energy of a photon, you can calculate it by using E equals to h times F, where h is Planck's constant, and it has a rough value of 6.63 times 10 to the power of minus 34 with a unit of joules per second. And F is the frequency. Now, the frequency of a photon, which is a particle, can be calculated in a variety of ways, because sometimes in the questions you're not given the frequency. Sometimes they give you the wavelength. So if they give you the wavelength in a question, how can you calculate it? Well, of course, they give you the wavelength of a specific part of a specific type of light with, for example, maybe like 600 nanometers, 400 nanometers, and you have to convert those nanometers or those wavelengths into frequency. So you do that by saying that the speed of light c is equal to lambda times f. So you can rearrange this for f, and f becomes c over lambda. And you can actually put that instead of the f over there in the first equation, and so E becomes hc over lambda. This is the case if the wavelength of light is given to you instead of the frequency of light. For example, if they ask you to calculate the energy of a photon and they give you the wavelength of that light, you can use this equation to calculate its energy. After this, obviously, you talk about the photoelectric effect. The photoelectric effect has the work function, which is very similar to the first equation. Phi is equal to h times f. If you remember, the work function is basically the amount of energy required to release photoelectrons from the surface of a material. And so unless you are not able to reach that the work function or that minimum energy, no photoelectrons are going to be released from that metal. And you can also calculate the threshold frequency, which is the minimum frequency required for photoelectrons to be released, by simply doing a rearranged version of this. FO is the work function divided by H. Further on, once you learn about the main topics regarding, the photoelectric effect and the energy of a photon and all these things, keep in mind you also have to know that you can calculate the charge of the fundamental particle electrons by multiplying N, the number of electrons, by E, which is the charge of one electron. So here Q is measured in coulombs, and E has a constant value of 1.6 times 10 to the power of minus 19 coulombs. That's the charge of one electron. Nonetheless, after you learn about these things, you go ahead and you learn about de Broglie's wavelength. De Broglie's wavelength is lambda equals to h over p, where p is the momentum of that particle that is going to get diffracted. So the whole idea behind de Broglie is that matter or anything that we conceive to be like an electron or a particle can diffract if it goes through a very narrow slit. And so it can behave like a wave, and because it can behave like a wave, it does obviously have a wavelength. And because this particle has speed and mass, it can obviously have momentum. So you can calculate the de Broglie wavelength of any particle simply by dividing Planck's constant over its momentum. So h over p, by the way, p is mass times velocity because it's momentum. Momentum is the product of mass and velocity, so h divided by m times v is also another version of this formula. Usually with de Broglie's wavelength, you'll be, in the quantum physics part, you will be mostly asked to kind of just calculate, for example, the wavelength in some scenarios, or maybe like they will give you the speed of a particle and they will ask you to calculate the wavelength. But if you go to the particle physics parts of the A levels, you will be asked to, for example, sometimes calculate the wavelength when they give you the voltage, because you have the equation kinetic energy being linked to voltage. But we're not going to be talking about that today. This is basically going to be the summary of what you need to know in order to solve a question. And we're going to go ahead and quickly kind of take a look at a very difficult question, I would say, that came up in the one of the newest A-level exams. And so you get a better idea of how to solve questions. So over here, it says that ultraviolet light is incident into a zinc plate. So obviously that's an example of, photoelectric effect. The first thing they want to ask is state what is meant by the work function. Well, you guys just understood now that the work function is the minimum energy. It's the minimum energy required to release photoelectrons. So if you're not clear on the topic of photoelectric effect, basically we have these types of metals and like cesium, potassium, magnesium, and we know that in metals we have these free electrons. The whole idea behind the photoelectric effect is if light has enough frequency and enough energy, it can hit the surface of a metal, and these electrons have something called a work function. If the work function of it is met with the light, that means that if light has enough energy to kind of pay a ransom fee to the metal, and the ransom fee, by the way, is this work function. For example, it could be like 2.3 electron volts or like 4 electron volts. If the light has enough energy, then it's going to allow these electrons to get released from that surface. And these electrons are going to come off with a little bit of speed, and so they have kinetic energy. And at the same time, you can find out about the kinetic energy of these particles simply by subtracting the energy of the first photon, the photon that hit the metal, because this part is the energy of the photon, by the amount of work function, which is the ransom fee that has to be paid to the metal itself. Now, the second question that is given in this a question is very difficult. It says that ultraviolet section of the electromagnetic spectrum can be split into 3 parts: UVA, UVB, UVC. The range of these wavelengths are given, and the minimum de Broglie wavelength of the electrons is actually given. So right now, as you can see, we are actually kind of mixing up the photoelectric effect with the de Broglie wavelength, and now they're asking us to deduce whether the ultraviolet light incident upon the zinc plate is UVB, UVA, or UVC. All right, so let's kind of recap this question and think about it a bit. The first thing you have to understand is they're asking us to find out the wavelength of the original light, but we're not given anything regarding the light that we are talking about. For example, we're not given the frequency of the light, we're not given the energy of the photons, and we're not given even the velocity of the photons. So we have to work our way from the beginning. And the first thing you want to do is you want to actually calculate I'll go down here. I'll write some of this stuff here. So the first thing you want to do is actually go ahead and calculate the momentum of the particles, because we have the de Broglie wavelength here, we have the lambda here, and we also happen to have the Planck's constant in the first question. So we know that lambda, we just learned, is h over m times v, where mv is momentum. So we're going to calculate momentum in an effort to calculate the speed of the light. I mean, the speed of the electrons that are going to be released. So P is going to be h divided by lambda. If we rearranged this equation, lambda h over p, we can get p is h over lambda. Now h is 6.63 times 10 to the power of minus 34, and that gets divided by lambda, which is given in the question. All right, now if you divide these two numbers, you're going to get approximately 4.42 times 10 to the power of minus 25 kilograms meters per second. That's the unit of momentum. Okay, so now that we have the momentum, we can actually find the velocity of the electrons, right? So velocity of electron is going to be the momentum divided by mass. How? Well, we know that momentum is mass times velocity, right? So velocity is simply going to be P divided by M if we rearrange it. So we can divide the momentum by the mass of one electron, and that will be equal to approximately 4.85 times 10 to the power of 5 meters per second. All right, so that's going to be the velocity of the particle itself. I mean, of the electron that's getting released. Now, we can find the kinetic energy of the released photoelectron next by simply multiplying 1/2 times mv squared, where the v is the velocity that we just found, and m is the mass of one electron. So 1/2 multiplied by 9.1 times 10 to the power of minus 31, multiplied by the velocity of the object. I'm just going to write V because it's the same as the one above there. Now, we're going to calculate that. All right, so the value is going to be 1.07 times 10 to the power of minus 19 joules. All right, so now we have kinetic energy. Let's recap everything. We found the velocity of the particle by using its momentum. We found its kinetic energy. Now, if you recall, we also have the work function in this question, but it's given in electron volts, and you have to convert those electron volts to joules. So you have to multiply 4.3 by 1.6 times 10 to the power of minus 19, and that would give you the work function in joules. So the value is 6.88 times 10 to the power of minus 19 joules. That's going to be the work function of this metal, the zinc, in joules. All right, now let's wait for a second. We found the momentum, we found the kinetic energy, and we have the work function in joules. So what's next? The next thing that we can do is we can use the equation that we just learned in the question before. Kinetic energy of a particle is equal to the energy of the photon minus phi. All right, let's think about this for a second. We're trying to find out the energy of the photon in an effort to find the wavelength of the photon. So we can deduce whether it's ultraviolet C, ultraviolet B, or UVA. So here's what we're going to do. We're going to rearrange this for the energy of the photon. And the energy of the photon is going to be equal to the kinetic energy of the particle plus the work function. If we take this to the other side, right? If you take phi to the other side, it becomes positive. So the energy of the photon of light is going to be equal to the kinetic energy, 6.88 times 10 to the power of minus 19. Sorry, that was the work function, plus the kinetic energy, which is actually 1.07 times 10 to the power of minus 19. And so the energy of the photon can be found, which is roughly equal to a value of 7.95 times 10 to the power of minus 19 joules. Wow, that was hard. So now we found the energy of the photon. What's next? We can find the frequency of the photon, then find its wavelength. We're going to do that here. So I'm going to go down. Let's draw a line here. Okay. To find the frequency of the photon, we know that energy of a photon is equal to frequency times Planck's constant. We can rearrange this for F by dividing both sides by H. So F is equal to E divided by H, where E is 7.95 times 10 to the power of minus 19, divided by Planck's constant. So F is going to be equal to, let me calculate that, approximately 1.2 times 10 to the power of 15 hertz. That's going to be the value of the frequency. And last but not least, we know that the speed of light c equals to lambda times f, right? So in order to find the wavelength of this speed of this frequency of light, we just need to divide the speed of the light by the frequency that we just found. So the whole thing, the whole process was just to find the frequency. And once you have the frequency, you can use c equals lambda f to find the wavelength of light. So the speed of light is 3 times 10 to the power 8. It's a constant number. And f, which is the frequency, is 1.2 times 10 to the power of 15. And that would give you a value of, if you were to divide those two numbers, approximately, wait, let me do that one more time. So 3 times 10 to the power of 8 divided by 1.2 times 10 to the power of 15. All right, we'll give you a value of 2.5 times 10 to the power of minus 7 meters. And if you were to move this decimal place 2 places forward, you would get 250 times 10 to the power of minus 9, which is 250 nanometers, which means the light that originally hit the zinc surface was UVC because the range of its wavelength is between 200 to 280. So because the range of wavelength of UVC is 200 to 280, the light is UVC. That's how you can deduce this question. So don't get thrown off by the difficulty of this question. It's just got a lot of steps. You have to be able to analyze it well. And once you do lots of questions and practices like this, you're going to be able to do them in the future. But you need to understand, sometimes students make mistakes they combine the wavelengths of the electron with the wavelengths of the light, and those are things you have to be careful about, because initially they've given you the wavelength of the electron. So from the wavelength of the electrons, you cannot find the wavelength of the light itself. You have to find the frequency of light first and then its wavelength. And then make sure you don't make any calculation errors. And also some of the constants, for example, will always be given to you. For example, the speed of light is always given 3 times 10 to the power of 8 meters per second. The mass of an electron is in the formula sheet. It's just 9.1 times 10 to the power of minus 31 kilograms. And if you want to convert from electron volts to joules, you have to multiply by 1.6 times 10 to the power of minus 19 joules. You can actually watch a video of mine I have from electron volts to joules, which is a very common type of conversion you need to know in quantum physics. So that's it for today. I hope that you understood how to do this question. Make sure you do a lot of practice, and good luck for the future.